All right. Hello, everyone. I'm the mechanics lead for Team 1418, and I'm here to to introduce Mike Anderson to talk about Roboreal functionality and programming. Uh, Mike Anderson is currently a principal embedded security engineer for the MIT RE Corporation, and he's worked with Team 116 for the past 12 years, specializing in controls hardware and software. Take it away.
Thanks, everybody. Let me see if I can get this up here and get it going. Hi, thanks for the introduction. As mentioned, my name is Mike Anderson. You'll see my email address here in case you need to reach out to me. I'll be happy to try and answer any questions. I am a mentor at Team 116 out at Herndon High School. Have been working for quite some time with FRC systems, and in this particular presentation, we're going to focus on how we get your RoboRio put together, your control system wired, and the software ready to run so that you can run your very first robot program. So we'll talk a little bit about the basic FRC control system, discuss sensors from the perspective of both absolute and relative sensors, and then we'll hit some of the more common sensor systems that we'll encounter in FRC, including cameras, limit and position sensors, speed sensors and their associated encoders, distance and direction / tilt sensors, and then we'll talk a little bit about how we would interface to these sensors so that you can bring them into the robot. We'll then transition into a discussion of installing the RoboRio software in the development environment, and we'll finish up by talking about how we build code and deploy your very first robot program, and we'll show you an example of that. We'll finish up with a brief summary and wrap things up. This is an example of the 2022-2023 FRC control system. We'll start over here on the right-hand side with the power distribution panel, the PDP. We bring in the battery input into the power distribution panel, and then this panel is used to distribute power throughout the rest of the system. The device of most importance here is the RoboRio. The RoboRio is the base computer that's used in FIRST. Without the RoboRio, of course, we can't drive the motors or the motor controllers, things of that sort. So this is a very important piece. We'll talk a little bit more about this coming up. This particular device can be used to interface to servos. We can talk to analog sensors, relays. Of course, we have the robot signal light, which is required for FRC robots. And then we have the digital sensors. These are digital IOs. You can be either an input or an output. We also have power coming in to the top of the RoboRio. And we'll talk again more about this here in just a moment. But one of the key pieces off the RoboRio is the controller area network, otherwise known as the CAN bus. The CAN bus comes into motor controllers. It can then also be daisy chained to the pneumatics control module and ultimately back into the power distribution panel so we can then read how much power is being drawn by various motors, for instance, or the motor controllers. The pneumatics control module is used to interface between a pressure switch and a compressor. The pressure switch then measures the amount of pressure in the storage tanks and will then turn on or turn off the compressor as needed. Through the CAN bus, we'll be able to send commands to turn on pneumatic solenoids, which will then either extend or retract pistons, air-powered pistons, that can be used for lifting robots and extending arms and things of that sort. We also have a voltage regulator module here. The voltage regulator module provides both regulated, both 12 volt and 5 volt to various circuits that may need it if you're using an Arduino, for instance, or if you're using an IP camera like you see here. We also have over here in this box, we have the operator console, otherwise known as the operator interface. The operator interface is at the driver station and controls the robot remotely using a joystick, the laptop supplied by the team, and that goes into an access point, a Wi-Fi access point, which then drives the RoboRio by sending it commands via this bridge. Here we see a more detailed picture of the RoboRio. Along this side over here, we see these things labeled PWM. Those are pulse width modulation controls. These can be used to drive servos or some of the earlier PWM motor controllers, like the Talon SRs. We have the reset button and the user program button. Very rarely ever use that button here, but the reset button is used often to reboot the RoboRio. Along the bottom, we have the analog interfaces. This is analog in. We'll talk a little bit about digital versus analog a little bit later. We have relays. These are typically either on or off. We have the robot signal light interface, and then we have digital IOs over here. The digital IOs are either an input or an output. We have RS-232, I2C, which are used to interface to sensors. We have the CAN bus along the top here. There's the input power for the RoboRio. We have a USB-B. This is typically used to program the RoboRio. Then we have USB-As, which are used to interface to things like USB cameras. The primary network interface into the RoboRio is via the Ethernet here. This will typically be installed or cabled into a bridge of some sort, a Wi-Fi bridge. We also have the SPI bus, which is the serial peripheral interface. This is another mechanism that can be used for interfacing to sensors. And then we have a number of LEDs, which tell us basically the status of the RoboRio. Here in the middle, we have a custom electronics port, otherwise known as the MXP port, which is an extension port that's available. There are certain off-the-shelf boards that are available that plug into this in case you need to have more digital IOs, more PWMs, or some other way of extending the RoboRio itself. Here we see the RoboRio version 2. This is the latest and greatest version of the RoboRio. It is essentially identical to the original version of the RoboRio with the exception of a couple of things. First of all, it adds an SD card slot here. So rather than booting off of the local firmware inside of the RoboRio like the version 1, this boots from the SD card. The other characteristics that make this RoboRio a little bit different, it's faster. It moves from 666 megahertz dual core Cortex A9s for ARM Cortex A9s over to 866 megahertz Cortex A9s. So it's a little bit faster, has more memory, and of course with the SD card slot you can have more storage, which allows you to collect logs and other pieces of information that may be of some use to you in debugging your applications. To further amplify the differences between the RoboRio version 1 and version 2, of course, we talked about the SD card. It does have some additional storage and an option for a gold copy of the boot code so that you can restore your program back into the RoboRio in about 23 seconds or so in the event that you accidentally wipe it out while you're in the pits getting ready for competition. That does happen on occasion. Version 2 has a lower brownout voltage. It drops down to about 4.5 volt, whereas version 1 was a 7 volt brownout. We talked about the processor cores jumping from 666 megahertz to 866 megahertz, so they're about 200 megahertz faster, about a third faster. The RAM in the version 2 is double that of the RAM in the version 1. We jump from 256 megabytes to 512 megabytes. And the storage, of course, is significantly larger owing to not only the larger FPGA field programmable gate array, which is used for things like controlling the shaft encoders and things of that sort that we'll talk about. as well as the micro SD storage that is available to us. So there's quite a bit more storage options. Both version 1 and version 2 will be legal for the foreseeable future. Version 2 was included in the rookie kit of parts. It's also available from AndyMark for about $485 if you happen to be able to find it in stock. That, of course, has been a bit of a problem since the pandemic, but hopefully that'll ease up a little bit as we get a little bit further away from the issues caused by the pandemic. Here are some of the new parts that are available from Rev Robotics as an option to the cross-the-road electronics parts in the original FRC system. We see here the power distribution panel. This is the new PDP. It has the advantage that all of the circuits are capable of operating at 40 amp versus what we saw in the original power distribution panel. There are also additional slots that are available here. This is a little bit easier to work with as well because of these different connectors. This simplifies the ability to plug wires into and out of the power distribution panel. And there is a display in the power distribution panel of the voltage, which is also new for the Rev Robotics parts. The pneumatic control module from Rev is a little bit more sophisticated than the one that originally came from Crossroad Electronics. This one has additional pistons that can be used. This actually supports up to 16. That is quite a bit better than what we had with the original power distribution, or rather pneumatic control module. There is also a power over Ethernet injector here that is used to interface between the RoboRio and the radio that's used to interface to the field control system. The power over Ethernet injector here allows us to power the radio directly from the power distribution center rather than having to plug in a separate power module here. That makes the radio a little bit more reliable and less subject to shutting off in the event that the robot may get hit by another robot. Now that we've had an opportunity to take a brief look at the control system, we're going to start talking about sensors. These sensors can be used to take some of the burden off of the drive team by making the robot do things more automatically. We also have other issues that we have to deal with here when we're talking about sensors. Sensors are made to make measurements. Now, these measurements can be either absolute or relative measurements. An absolute measurement would be something like speed the shooter wheel up to 3,500 RPM. Whereas a relative measure would be spin the shooter wheel faster, 25% faster than it was before. So relative are always going to be relative to what the system is doing now versus absolute, which will be true no matter where the robot started or what direction it's pointing or anything of that sort. So absolute things are sensors that will be either on or off. Relative could be a voltage coming into an analog sensor. Whether you're using absolute or relative measurements depends totally on the application. So as just mentioned, the reason we would use sensors is to help take some of the burden. Was there a question?
Nope, I think we're okay, Mike.
Oh, okay. Off of the drive team. Given some of the games that we play, that can lead to some fairly complex robots, which can be almost too difficult to manage even for the two-person drive team. So sensors help kind of loosen that burden off of the drive team and make the robot do things automatically, like targeting or turning around or something along those lines. Getting the right sensors can make the robot simple to control during the game. And recent games make it difficult for the drive team to even see the robot on the opposite side of the field because there may be some obstacle in the way. So sensors can make controlling the robot remotely that much easier. One of the more common sensors is a simple camera. These cameras can either be a USB or an IP camera, and they can typically be enabled in the robot with just a couple of lines of code. Virtually all robots can take advantage of the camera, even if it's just to show the drive team what the robot is actually seeing. However, in much more sophisticated uses, the camera can actually do target recognition, can do auto targeting, can do color detection, and a whole lot more. There have also been some significant advancements in the WPI lib, which is the software module, the software library that's used to program the RoboRio. And some of those enhancements include AI and machine learning enablement that allow the robot to make decisions kind of autonomously without the user having to really force it to do anything. This is particularly important when you take a look at this picture that we see here. This is a picture that is seen by the camera of targets that were being used. We were actually shooting frisbees through these little slots here in one game. And this is retroreflective tape. So when you shine a light on this retroreflective tape, the light comes back and will then be reflected in whatever color you happen to show on the retroreflective tape itself. So in this particular case, this was blue. A lot of times that will be green. There are also very specific cameras, such as the ones called the limelight cameras. Limelight cameras have a very bright green light on them that shows up quite well in these retroreflective tapes. And those particular cameras have built into them algorithms for doing auto targeting and image recognition. So they're very powerful cameras. They're relatively expensive, but they do have the advantage that they automate a lot of code and take that programming burden off of the software team. Here we see an example of a fairly common set of sensors found in FIRST robots. The first is a limit switch, which, as its name implies, is typically used to measure the extreme motion of an arm, let's say. Whether it's fully extended or fully retracted. If it's fully extended, it triggers the switch, and then in software we can read that signal to determine whether or not the robot arm has reached its full limit. This is a digital sensor. That is, it's either on or off. And as a digital sensor, it would be wired into the DIO ports on the RoboRio. We also have another type of sensor called an analog sensor. This is a potentiometer. And in the potentiometer, we have voltage coming in, voltage going out, and then we have this thing called the wiper, the center rotator. As this individual arm moves around on this track, we then get varying voltages out of this. Because there are any number of voltages that could potentially be represented by this particular signal, this is referred to as an analog sensor. And an analog sensor would then be wired into the analog in ports on the RoboRio. Another sensor that is not quite a digital and not quite an analog sensor is the position sensor. And this particular sensor is using the Hall effect, which is a small magnet here. And as this magnetic disc, as this little disc spins, it's not necessarily magnetic, but as this disc spins, when it comes across this little gap, it then increments the sensor here. So this is a counter, which can be used for a tachometer or being able to count how far a motor has turned. Another option allows us to measure the gear teeth as this particular gear turns. So if, for instance, this gear had 25 teeth on it, if we've counted 25 pulses, we know that we have turned one full revolution. So this is also wired into the digital input, the digital I/O on the RoboRio. So it is technically a digital input, although it's used not just simply for an on or off, it's used to indicate a count of some sort. Again, if this is attached to a shaft, a motor shaft, then this can be used to determine how far something has gone or how fast it happens to be turning. Very useful for tachometers in shooters, for example. Speaking of motor shafts, another common sensor is the quadrature encoder. The quadrature encoder can tell you how far something has moved and in what direction that movement has gone. So, for instance, we see here there are two different inputs. There's an A input and a B input. These are both digital inputs, by the way. If the A leads the B, then we know we're going clockwise. If B leads the A, we're going counterclockwise. And this allows us to be able to keep track of what direction the wheels are actually moving. So we'll often find these things attached to wheels of some sort, maybe the drive wheels for your robot, and they'll be incorporated into some of the more modern brushless motor controllers like the Rev Robotics Spark Max and the Cross the Road Electronics Falcon 500. These are very important, especially in autonomous mode, which is at the very beginning of the game. You'll have particular scoring values. For instance, if you can cross this line, you'll automatically score 5 points or whatever it is in the game, and the line happens to be 5 feet away from the back wall. So if we know the circumference of the wheel and we know how far the wheel has to turn in order to be able to move 5 feet, we can then count the pulses coming off of the shaft encoder and then guarantee that we've in fact crossed the line that will get us the points. This is a much more reliable mechanism than simply turning the motor on, running it for some number of seconds, and hoping for the best. Another sensor that we commonly encounter are distance sensors. Anytime we have a circumstance where we're trying to measure the distance between the robot and, let's say, a shooting target of some sort, by knowing that distance, I then know how fast to spin the shooter wheel up so that I can guarantee that I can then sink the ball or whatever the game piece is into the target. These all typically work in the same way. They're referred to as a time of flight sensor because we'll take either a light pulse, an ultrasonic pulse, or even a laser pulse. We will bounce it off of the thing we're trying to measure, and the amount of time that it takes for the pulse to come back to us will then allow us to measure how far away that particular device is. So if I know the speed of sound at sea level, I can then use an ultrasonic sound pulse to send the sound pulse out, have it bounce off the wall, for instance, and then come back to me. I measure that amount of time, and by knowing the speed of sound at sea level, I can then calculate how far away that particular device is. Now, common distance sensors will use either infrared light, or they'll use ultrasonic, which is above the hearing range of a typical human, although dogs can often hear it. There is also the potential for using what's called a Class 1 laser, and the Class 1 lasers are eye safe, and therefore they're FRC legal. These are also referred to as LiDARs. And we'll show you pictures of what these things look like here in a moment. The thing that we have to be aware of is that not all distance sensors are created equal. In the case of ultrasonics, they may be limited to 10, 15 feet. In the case of infrared, they might be limited to just a few centimeters. Or in the case of the laser, it might be as much as 35 to 40 feet. It just depends on what your requirement is as to which one of these individual time of flight sensors you would pick. Here we see some pictures of some of these sensors. This is an ultrasonic sensor that has one emitter and one receiver combined into one particular device. This is from a company called Maxbotics. We have infrared sensors. So we have a transmitter and a receiver sensor here. So this sends out an infrared pulse, and then the amount of time that it takes for that infrared pulse to bounce back, that's going to determine the distance. Because this is infrared, you can't see it with the human eye. However, Android phones can actually see the pulse. You'll see it show up as a purple light in the sensor here. It turns out that for whatever reason, Apple phones can't do this because Apple has disabled the ability to sense infrared in their camera phones for various reasons. Here's another example of an ultrasonic sensor. This one happens to have two separate in a transmitter and a receiver here, as opposed to this one where they're combined together. We see a similar sort of thing over here in this laser imaging system, this laser rangefinder. We have a transmitter on this side and a receiver on this side. This particular laser happens to be attached to a servo, which would then give it about 180 degrees worth of movement. So it then means that it can kind of search around on the field to try and find something of interest. The thing that you have to be aware of is that in the case of ultrasonics, the signals tend to spread out pretty quickly. Similar thing for the infrared sensor, whereas the laser is a point at some distance. So one of the problems that you have with these laser-based rangefinders is that they can be almost too accurate. So for instance, if you happen to be looking at a door and the laser pulse goes through the door and hits the back wall, then you're actually measuring the distance to the back wall rather than the distance to the door. So the ultrasonic would be not as accurate. It would then measure the distance to the door, to the doorway, and not measure the distance to the back wall inside of the doorway. So you do have to be aware of the capabilities of these individual sensors and then pick the right one for your particular application. A very common sensor that's used in FRC robots are direction sensors. These are typically going to take the form of either a gyroscope, a magnetometer, or an accelerometer. Gyroscopes measure the rate of turn, and WPI-lib has a set of functions that are integrated into it to determine the angle of the robot relative to the starting position using the gyro class. Magnetometers are also known as digital compasses. And a digital compass can be impacted by a large magnetic field, such as what we see with the compressor or motors. Therefore, magnetometers typically aren't of much value, even though it's a compass and you could potentially use it as an absolute measurement to determine where north is, for instance. It doesn't have as much value in FRC applications because of the existence of these big motors that we'll typically have on the robot. Another one of the sensors that was mentioned on the previous chart is the accelerometer. The accelerometer measures the force of gravity, and normal gravity at sea level is defined to be 1g. At 1g, we know that we're completely level. So if we were to take a look at this particular example, we have a 3 degree of freedom sensor. That is, it has a forward and back, it has a left and right, and it has an up and down. If we were to move from left to right in the vertical direction, in the up direction, or in the down direction, it turns out, this is referred to as roll. If we were to measure the distance from left to right, and this left to right is turning, that's called yaw. If we're measuring from front to back, and that is moving, that's called pitch. So we have roll, pitch, and yaw, which are very common terms that are used in aircraft, drones, and things of that sort. This particular sensor can be very useful in certain types of games. For instance, in this example, we see the 2012 Rebound Rubble game, and with this particular game, the robots had to balance on this teeter-totter at the end of the game. We could then use the accelerometer to determine whether we were tilted And by knowing that we're tilted, we can then move back and forth on the teeter-totter to try and get it to be relatively level. There also can be used to detect impacts and make adjustments to gyros to correct for gyro drift. There's usually anywhere from 2 to 3 degrees worth of gyro drift in the couple of minutes of the game. And if we got slammed by another robot, then that could potentially knock the gyro out of alignment. So we can use the accelerometer to measure that impact and then be able to make adjustments for the drift in the gyro as a result of being hit by another robot. It turns out there is a 3-axis accelerometer inside of the RoboRio, so you don't even have to attach any external sensors to take advantage of this particular type of sensor. Just use the built-in accelerometer inside the RoboRio itself, and the WPI lib has library functions that allow you to take advantage of that accelerometer. If we combine the gyro, the accelerometer, and the magnetometer together into one particular unit, this is often referred to as an inertial measurement unit, or an IMU. This allows you to know pretty much where your robot is in the physical world and allows for fairly precise navigation. This is the type of thing that's typically used in drones, for instance, or in spacecraft. Here we have an example of the NavX MXP. This particular unit plugs into the MXP slot on the RoboRio, and it has an IMU built into it, and it even has its own little microcontroller built into it to talk to the IMU. And this microcontroller then brings additional digital IOs. It brings additional interfaces across the board here that can be used to expand the capability of the RoboRio. Another one of these devices is known as the Crossroad Electronics Pigeon. The Pigeon is a CAN bus based IMU as opposed to one that plugs into the RoboRio itself. In general, in order to get the most precise location information, your best bet is to mount the IMU in the center of the robot. This is not easily done if the IMU is mounted to the RoboRio, because there's no guarantee you can mount the RoboRio in the center of the robot. However, the Crossroad Electronics Pigeon sensor is connected via CAN bus, and we can then use the CAN bus cabling to move that sensor into the middle of the robot. With the IMU, it's going to be pretty easy to maintain a heading even if we get hit by other robots. So because in that particular case, we're probably not going to get that much drift out of the IMU, even though it is a gyro. And because we won't get a whole lot of drift, if we get hit by another robot, we can always just readjust and get back on the same heading. So if we know that we need to go a particular direction across the field, we can use the IMU to keep us going straight. This is also handy if we have gearboxes that are not quite the same, or motors that are not quite the same. The IMU can be used to keep us going straight. It can also be used if we have to do something like turn 90 degrees or turn 180 degrees. We can use the gyro to then tell us how far that is, and then we know that we've turned the amount of distance or in the direction that we need to go. In many cases, we also need to be able to kind of offload the robot software and have the motors operate in what they refer to as a closed loop control system. There are several of these motor controllers like the Crossroad Electronics, the Talon, SRX, Rev Spark Max, and others that have inputs, and these inputs can be used to tie either into an analog input if we were using a potentiometer. We have quadrature inputs if we're using a shaft encoder. We also have limit switches, forward limit switch, and a reverse limit switch. The nice thing about these is that if you're using these forward or reverse limit switches, for example, you don't have to write any software in order to have the motor controller stop when the limit is hit. So if I've got a motor attached to a robot arm, and I'm lowering the robot arm, if I hit the forward limit switch, then I know to stop the motor controller. I don't have to sit there in software and say, have you gone far enough? Have you gone far enough? How about now? Have you gone far enough? I can just simply say, start moving forward, and then when the limit switch gets triggered, it'll automatically stop the motor controller. This is referred to as closing the loop with the motor controller. So here's an example of a shaft encoder. This is a quadrature encoder being attached to a gearbox. The output from this quad shaft encoder will then go into the quadrature A and B inputs of this motor controller, and then allow the motor controller, I can then say, go 300 pulses in the forward direction, and it will actually count the pulses and then stop the motor automatically when it gets to the destination. Very handy and more of an advanced application. But if you can take advantage of some of these closed loop control mechanisms in the hardware, you can simplify the software dramatically. So we've talked about a number of sensors up to this point. How do we interface these sensors into the RoboRio? The WPI lib has got a collection of interface support libraries, and we can talk to individual sensors via serial port, the inter-IC communications bus, that's called I2C, the serial peripheral interface bus, or digital IOs or analog inputs, just to name a few interfaces here. The advantages of the SPI interface is that it's faster than I2C, but I2C is very simple to wire. It only requires 2 wires, whereas SPI requires 4. When you're selecting a sensor, you need to make sure you know what kind of interface it has and compare that to the number that you currently have available on the RoboRio. If I'm trying to wire the SPI bus, for instance, SPI bus only supports 4 peripherals. So if you have a 5th peripheral that talks to SPI bus, then you'll probably have to use some extension, maybe using an Arduino or a Raspberry Pi as an auxiliary processor to sample that particular sensor and then communicate via Ethernet into the RoboRio itself. You also have to make sure that you allow for a power and a ground return. Most of these sensors will require either 5 volt or 3.3 volt. You need to make sure that you have the right voltage. As it turns out, the RoboRio is actually a 3.3 volt system, but it is 5 volt tolerant. So you can hook up 5 volt sensors to the 3.3 volts and expect them to work without burning out the RoboRio. But you do have to be aware of how much power it requires and make sure that you have not only the signal wires, but also the power going to and from the device in order to make sure that it works. In order for us to be able to load the initial firmware onto the RoboRio or use the driver station, we have to install the National Instruments code. The National Instruments code in this particular case is focused on the FRC game tools. And this interface you see here, this is actually a link into the WPI lib code. If you just simply Google or use whatever browser you happen to be partial to, and just look up FRC software installation, it will lead you to this particular link out at WPI lib. You will install, you'll basically have to download the National Instruments code. This is several gigabytes, so it'll take you quite a while to download this. And then it's probably best if you uninstall any previous versions. Let's say you have an old laptop from last year. You'll want to uninstall the National Instruments code first, the old code first, and then install the new code. This will typically take anywhere from 10 to 20 minutes to install, depending on whether you have solid state drives or rotational drives. And it could potentially, of course, take longer if you have to uninstall the previous version. This will install the FRC driver station application, as well as the RoboRio imaging tool, the modem imaging tool, and bring everything up to the latest release of the firmware. You'll then need to, of course, program that into the RoboRio or the modem or whatever, and then, of course, reboot your local laptop after you've installed the National Instruments code so that it updates everything. Unfortunately, this only works with Windows. National Instruments does not supply the same solutions for both Mac OS and or Linux. So in this particular case, if you're going to use the FRC driver station on a particular laptop, it must be a Windows laptop and nothing else. Here's a snapshot of the 2022-2023 driver station from the FRC games that were installed when we installed everything from National Instruments. You'll notice down here in the bottom, this is the driver station. And in the driver station, we'll have several different modes of operation: teleoperated, autonomous, practice, and test. The teleoperated is the section that the driver and the drive team are actually going to have control of the robot. Autonomous is what its name implies. If you're trying to test out your autonomous routines before you get into teleoperated mode, you can then click on the autonomous button, and then it will execute the autonomous code when you press the enable key here. Practice allows you to run through the entire system, where it starts off with autonomous and then switches over to teleop. And then the test button here is to test various pieces of code. You'll see the PC battery and the percentage of CPU being used by the PC as it executes the driver station code. We have the team number here. This is either going to be a red or a blue, owing to the 3 teams on the red alliance or the blue alliance. So this allows you to select what position you're in case your autonomous routine happens to be very specific to a particular location in the field. Then you can actually set that here. You'll see when you have a connection to the robot, you will see this will light up green and show you the battery state of the robot. When we have communications with the robot, we will see this turn into a green light, a green LED, if you will. The robot code, if this is green, then you have robot code loaded on the robot. And if you have your joysticks plugged in, this will also turn green. So if we have a robot connected, we should see all 3 of these LEDs turn green. I will caution you that oftentimes you will think you're connected to the robot, but for whatever reason, communications and or the robot code lights do not light up. That is more than likely because you have a firewall in place. So you will, on that particular laptop, you will need to disable the firewalls, whether you have the Windows Defender firewall or you have Norton or some other type of firewall in place. You'll have to turn those off in order for you to be able to get communications to work. It turns out that the ports that are used by the field management system and the robot to talk to the robot drive station, unfortunately, will typically get filtered out by any individual firewall code. So you'll need to turn those off. Just make sure you remember to turn them back on if you're going to plug into the internet, because obviously they're there for security reasons. We see over here, this is where messages will pop up. So any messages that come out of the robot or out of the robot code will be printed here. We're currently seeing that we are team 116. You will have to set that inside of the setup option here, this thing that looks like a little gear. That by pressing that, you'll actually be able to get into the setup to be able to set the team number and other characteristics for what dashboard you want to have come up. We will also have this little entry down here, the thing that looks like the USB symbol. That's precisely what it is. If you click on that, you'll then see the configuration for the controllers, the game controllers that you have attached. These are typically either going to be joysticks, or they could, for instance, be Xbox controllers or PS4 controllers. All of those will work just fine with the driver station. We also have this bottom little lightning bolt here allows me to measure power coming into the robot, so we can kind of see what's happening. If the robot is bogging down for whatever reason, we kind of measure that. And any of these individual options here, when you select them, you will, if you're looking at the teleop, autonomous, etc., you'll then click the enable button, and then that will turn the robot on. Now, according to the normal FRC rules, we want to make sure that we announce to everyone when we get ready to press the enable. We'll typically say enabling, and then everybody knows to get their hands out of the robot so that nothing happens, especially if you happen to have the autonomous setup here. Clicking enable could potentially have the robot suddenly wake up and start doing things. We wouldn't want anybody's hand to get caught in that, so we would absolutely want to make sure that we let everybody know that the robot's being enabled. When you enable the robot, by the way, if you have the robot signal light hooked up, as you should according to the rules, that robot signal light will start blinking. That is the dead giveaway that the robot is active and people should stay away from it. Up here in the dashboard, this is the default dashboard that comes with the National Instruments code. We can select a camera here, and whether we have the IP camera or the USB camera, we can actually select it and then have that camera feed come back to this default dashboard. We can also keep track of joysticks, so these will light up when you press buttons on the joystick. This shows you the orientation of the joystick as you run. If we happen to be using the gyro on the RoboRio, then or a gyro connected to the RoboRio, rather, we'll be able to measure the gyro angles. And there are a number of other things that we could potentially do with this particular driver station. Oftentimes you will find teams using this as the default just to get started, and then they'll switch over to something called Smart Dashboard. And Smart Dashboard allow me to be much more selective about the kind of information that's displayed and how it's displayed. So I can have a camera, I can have readouts of sensors, the accelerometer. I can read the sensor out of the accelerometer and then display it on the Smart Dashboard, things of that sort. So you do have quite a bit of flexibility when dealing with the dashboard. This particular dashboard happens to be written in LabVIEW, which is the National Instruments native environment. But again, it's a good starting dashboard, but probably not something you would be using for doing any debugging or any particular development work with the robot. If you're trying to display logs and things of that sort, this dashboard is probably not going to be a whole lot of use to you. However, if you happen to have display statements, print statements, that kind of thing, those will typically show up here in the console output. We can also, these are the console messages. If we select this little squiggle, that happens to indicate it'll start reading information from the robot. So it'll show power as a running strip chart. It will show communications. If we're dropping packets and that kind of thing, we'll actually see that if we select this little squiggle. And the last one down here, honestly, I don't know what that one does. I don't think I've ever used it before. If we want to clear this output window, clicking on the little gear looking gizmo here, if we click on that button, it will then have a pop-up menu that'll allow me to clear the logs. So if I'm trying to make sure that everything is being kept straight from one run to the next, I can do that by simply clearing the log and then starting over. There are a few things you should be aware of with respect to the RoboRio. The RoboRio is an ARM-based computer, so it's equivalent to what you would see with your smartphones, for instance. The RoboRio runs Linux. There is a secure shell server available. You can use PuTTY on Windows or Linux or Mac OS in order to get into the SSH shell. This will allow you to log into the RoboRio directly and get to the command line of the RoboRio. Any file transfers that are used that happen between your development laptop and the RoboRio are done using the secure copy program. So it's a variant on the SSH protocol that allows you to securely copy files back and forth. Addressing for the RoboRio is done using the Multicast Domain Name Service, or MDNS. The name of the robot by default will be roborio-your team number-frc.local. So if you go to a web browser and you wanted to talk to the RoboRio's web server, then you would simply type in HTTP roborio-116-frc.local, and it would automatically find your RoboRio. But I will give you a word of caution there, and that is the MDNS doesn't necessarily work all the time, especially when you're on the field with the field management system. So the best rule of thumb when dealing with the RoboRio is to use a fixed IP address. You can do that by going through the limited function web server that's on the RoboRio and use that to set the IP address. Typically, the IP address will be your .2 address. So let's assume that we're talking about team 116. That would be 10.1.16.2. That would be the address that you would program into the RoboRio using this web server. And then the next time you reboot the RoboRio, it would automatically come up at that IP address. That has some distinct advantages because then you don't have to have the field management system search for the robot. That saves time and eliminates some of the causes of disconnects during the game. So absolutely take the time to program 10 dot whatever your IP address is. So if you were 1488, you would be 10.14.88.2 would be the address you would program in. Another word of caution, do not delete the RoboRio admin account or change its password. It's required to load your programs to the robot. And if you delete the admin account, then effectively you will have no way of loading code to the robot. So don't do that. From a programming perspective, there are several languages that are supported on the RoboRio. Some of them are officially supported by FIRST, and some are supported by the user community. So the programming environments that are available for the RoboRio are the LabVIEW code from National Instruments. We also then have both Java and C/C++. All of those are officially supported. Python is available, but it's not officially supported by FIRST. So if you have decided to use Python and you run into any problems, you'll have to go out to the Python community that supports FRC to see if you can get some help there. You won't be able to go to FIRST and look for help on any of the FIRST resources. LabVIEW is a diagram-based language. So you actually kind of use pictures in order to create your programs. LabVIEW is found in a kind of a limited environment for test instruments that's developed by National Instruments. In the real world, you very rarely find LabVIEW used outside of that particular use case. So most of the FRC software is going to be written in either Java or C++. Java, of course, is the same language that's required by the computer science AP exam, and C and C++ is the language that's used by almost all other languages. In fact, both Java and Python are written in C++. The operating systems, Windows is written in C, Linux is written in C, Mac OS is written in C, Most of the operating systems and lower level code is written in C, or its object-oriented equivalent called C++. So it tends to be faster. That is, it executes faster than Java. Java, of course, uses bytecode, and that bytecode has to be run inside of a virtual machine that exists on the RoboRio. This is typically not a big issue for FRC games. It could be a problem if we were trying to run a hard real-time operating system, but that's not the circumstance that we have in FRC. The FRC Linux version, as it turns out, is a real-time Linux version. The folks at National Instruments have created a real-time flavor of Linux that uses the real-time patch. But in our particular case, because our games are relatively short, they're only 2 minutes and 30 seconds for the most part, we don't usually run into any issues with the difference between Java and C++. So even though the two languages are very similar, it turns out that Java was derived from C++. Even the syntax for these languages is very similar. It's fairly easy to convert from Java to C++ and back. As it turns out, the WPI lib is originally written in Java and then translated to C++, so that you have support for both of those languages. The first supported development environment for these languages, for both C and Java at least, is the Microsoft Visual Studio Code tool. This particular editor is available for Windows, Mac OS, and Linux. The compiler is the open source GCC compiler, and that supports C++ 17 extensions. The C compiler itself is actually a cross compiler. That is, we're building on one CPU architecture, the x86, for a different CPU architecture known as ARM. Again, this is a standard approach for commercial embedded development, so this is nothing new. In the case of Java, the build system will actually run the Java source code through the OpenJDK, or the Open Java Development Kit, to produce Java bytecode, which is then downloaded to the RoboRio when you tell it to deploy. Now let's assume that you have just taken your RoboRio out of its box, or you're taking an older RoboRio that was used in previous years and you're going to reprogram it. You will no doubt have software that is probably out of date. You'll need to update it to run the current FRC software, because the development environment has interlocks in it that checks the version of the FRC code running on the RoboRio before it will allow you to deploy code that's running one of the newer versions of WPI lib. So part of the code that was downloaded from National Instruments includes the RoboRio imaging tool. When you launch the RoboRio imaging tool, it will bring up this little dialog that you see here. And this dialog shows the RoboRio that you're connected to, and it shows you its current IP address and the current image that's on it. This IP address is the IP address for the RoboRio that's connected via the USB interface. So the USB interface always comes up at 172.22.11. The RoboRio is .2 and your laptop is .1. The circumstance we see here, we see this format target. That's what you'll want to do. That will then wipe out the old RoboRio firmware image and put the new image in place. You, of course, will key in your team number, and you will see the image that it will ask you to program. So typically when we install the National Instruments code, it will install the latest and greatest RoboRio image that will pop up in this particular window. You select it, and then you tell it to reformat. And then it will take probably 5 to 7 minutes or so. You'll see a little progress bar. You'll see the RoboRio reboot. You'll actually hear it reboot on the USB, because it'll have the little Windows ding ding sound. This then lets you know that the programming is going along. And when it finishes, you'll get a little notification that says the programming is done, and you'll have to deploy code to the robot in order to run anything. That's, again, a fairly typical thing. Don't worry about the weird little messages that pop up. As long as everything finishes correctly, you should be fine. In the event that you're running, now this is the programming tool that's used for the RoboRio 1. The RoboRio 2 in previous years had an issue where this particular interface did not work. Unfortunately, the RoboRio 2, because it boots off of the SD card, it's programmed a little bit differently. And if you look inside of that software installation guide that I talked about earlier, that's on the FRC website, or rather at the WPILib website, it will walk you through the process. You'll actually use Balena Etcher. If you've ever programmed a Raspberry Pi, then it turns out that the RoboRio 2 is programmed in exactly the same way. You'll insert the SD card into your laptop. You'll run Balena Etcher. You'll point it to the image that you want to put on the RoboRio. It will then download that image to the SD card, take the SD card out of your laptop, plug it into the RoboRio, and you're ready to go for the RoboRio version 2. The next step to set your development environment up is you'll download the WPI lib from the GitHub site. Again, that'll be indicated in that software installation guide that I pointed you to earlier. WPI lib is now bundled with all the code that's required to actually build uh, source code into objects and download it into the RoboRio. It's about 2.6 gigabytes for the zip download, so it's pretty big. It can, of course, be downloaded from GitHub, as I mentioned earlier. We will look at the Windows installation and we'll kind of follow that through, but understand that there are install steps for both Mac OS and Linux as well. So even though you can't run the driver station under Mac OS or Linux, you can do development for the RoboRio under Mac OS and Linux. But just to simplify things, because most people will be doing a Windows installation, we'll kind of walk through the Windows installation version to give you an idea of what that looks like. Of course, as I mentioned earlier, the development environment for the RoboRio code is done in Visual Studio Code if you're using Java or C++. So one step in the WPI lib installation will ask you if you want to install the MS Studio code editor, and you do if you want to run either Java or C++. This, of course, does run across all the environments, Windows, Windows, Mac OS, and Linux. But Visual Studio Code Editor will then host the WPI lib extension, and this extension will then allow you to build code and deploy code over to the robot as well as debug code. The installation of Visual Studio Code will take about 10 minutes, and the installation will automatically install the GNU compiler. It will install the JDK if you're using Java, and it will install and adjust all the run paths for you. So it's a fairly clean installation. Unlike the National Instruments code, you do not have to uninstall last year's Visual Studio Code if you happen to have it already installed on the laptop. You don't have to uninstall the previous year. In fact, what it will do is it will keep the years separate from each other. So if you happen to have a robot that you're keeping, an older robot, for instance, that you want to keep for demonstrations, and it requires the 2020 code, then the 2020 code will still be preserved out there, and you'll be able to switch from the 2023 code to the 2020 code or what, and back and forth. Now, once you install Visual Studio Code, you'll also have to install the vendor-specific libraries for devices like the Rev Spark Max or the Crossroad Electronics motor controllers. These are vendor-supplied installers, So you'll actually have to go out to that website. That is the individual manufacturer's websites, the Rev Robotics website or the Crossroad Electronics website, and download the installation tool for that particular set of libraries. You then need to include that library into your application code via the editor. And I'll show you how that's done here in just a moment. So here we see an example of installing the WPI lib and Visual Studio Code environments. When we start up the WPI lib installer, there will be an option here for selecting and downloading the latest version of Visual Studio Code from the Microsoft website. When you click that button, it will automatically go out to the website and download the latest version and install it. Now Visual Studio Code is installed on your computer, and it then presents you with this WPI lib installer option, which now says, okay, I will install Visual Studio Code, the C++ compiler, Gradle, which is the build system for the WPI lib stuff, and of course the Java JDK. We'll also see tools and utilities, the WPI lib dependencies, and the Visual Studio Code extensions. Those Visual Studio Code extensions include the WPI lib extension. We then click Execute Install, and when we run that, it will automatically go through the installation process. Once we've installed everything, we can then start up the Visual Studio Code. In this particular case, this was the 2020 version, but the 2022-2023 version looks identical. We'll click on this and it will bring up the Visual Studio Code editor. If we take a look in the Extensions tab, we'll see WPI lib as one of the extensions. You can add additional extensions here, by the way. You can add support for GitHub if you're going to be using source code control, which I highly recommend. If you turn on some of those additional extensions, you can do some additional syntax checking and, of course, the interface to the source control module, the GitHub environment, and things of that sort. So this is basically what you're confronted with once you open up Visual Studio Code, and the next thing you want to do is to try and create a new example. So we'll walk through that as well. So by clicking this little W that you see over here on the right-hand side, it will then bring up the WPI lib environment, the WPI lib menu. And one of the first things we want to do here is we want to create a new project. So by highlighting create a new project, it'll then lead us through another series of prompts. So the first dialog box that pops up with the WPI lib project creator is whether you want to create an example or you want to create a template. In this particular case, we were creating an example, and you can then select which language you want, whether you want C++ or you want Java. And then the actual example that you want to be able to run. In this particular case, we're trying to instantiate an arcade drive, which uses a single joystick to drive the robot around. We will select a folder where we want to place the project into. This is typically going to be your documents directory. You can give it a name and it will automatically create this folder, or if you have an existing folder that you want to put into, say you want to have document/2022, then you can tell it select a new project folder, navigate into the 2022 directory, and then it will automatically create a project by this name. Make sure you also specify a team number that will be part of the metadata that's encoded in the project so that it knows to deploy to your robot and not somebody else's robot. Once we have all this stuff filled in, we'll click Generate Project, and then this will go through the process of generating the source code for us for the example, and it will then create and open the project so that we can now edit it inside of Visual Studio Code. So this is an example of the kind of code that we would see. We will see the arcade example here called out as the folder that's open. Inside of that, we'll have a source file. That source folder or source directory will then have the source code inside of it. If we double click on the source code, it will automatically open that source code up inside of the editor. We can then go in and start making changes that may be appropriate for our particular robot. Maybe we're using different motor controllers, or we want to add support for the accelerometer or something along those lines. Those are the kinds of things we would do here in this editor. You'll notice that we see this build successful down in this kind of terminal window. Uh, that happens automatically when you instantiate a new project like this. So we've created a project. It extracted the project out of their archives and then created the folder here in order to be able to execute the code or compile the code rather. Uh, and what it does is it automatically runs the build just to prove that the example is working, that it's actually building correctly. So if you try to instantiate one of these examples and you don't see this build successful in this terminal window, and that says that the example was probably corrupted in some way or it was broken as it came from WPILib. I have seen that happen. Doesn't happen very often, but certainly can happen. So you'll want to make sure that this build successful shows up. Even though we see some examples that it shows problems, in this case it shows 5 problems, this happens to be because the search for these header files wasn't done correctly. If you then turn around and tell it to update the search path, then it will automatically solve these problems, and then the number of problems will go down to 0. So let's take a look at how we would go about building the robot code. So we've made our changes to the files. We've saved our edited files. If you go to then build the robot code, so we'll click on the W, that little W icon in the upper right-hand corner, and then tell it that we want to build robot code. When we tell it to build the robot code, it'll then go out and invoke the compiler, and as it does the compile, it will basically run through the process and hopefully we will see a build successful down in the bottom. If we did not see a build successful, then if we scroll back up in the terminal window, we'll actually be able to see where the compile failed. So we'll see a line number and we'll actually see the failure message from the compiler. That then tells us where we need to go look so that we can try and make this thing right and get it to actually build the code. Once we have the code built, then we'll want to turn around and take another option here, which is to deploy the robot code. Now, as it turns out, if we tell it to deploy the robot code and the code has not already been built, it will rebuild the code. So oftentimes people won't bother with build robot code. They'll just simply tell it to deploy. And if it builds correctly, it will then deploy automatically to the robot. If it does not build correctly, then it won't deploy. So you do have some kind of protection there. A couple of other things we should probably look at here in this menu. We can check for WPILib updates. We can refresh. In this particular case, we're doing C++, so we can set the current the C++ tool chain, the compiler. We can refresh the Gradle search options here. We can create a new class. We can debug robot code, which will debug the robot code on the robot itself. We can import an old WPILib Eclipse project. This is from several years ago. We can install tools from Gradle Rio, manage the vendor libraries, or go into the WPILib command palette. We will, in particular, take a look at this Manage Vendor Libraries option because that's how you will install the third-party libraries from somebody like Rev Robotics or from Cross the Road Electronics. So before we can take advantage of the third-party libraries to run things like the Rev Robotics motor controllers, ArcMax, we need to install the third-party library into the project. So in order for us to be able to do that, we have to go out to the manufacturer's website and download their installer program. Once we've done the installation of their libraries, it will automatically copy their libraries into the WPILib build environment. Then we need to incorporate that into our application in order to be able to take advantage of the APIs that exist in that library. So we'll click on the W again in the upper right hand corner. We'll then bring this little editor down, this little pop-up down, and we'll select Manage Vendor Libraries. In selecting that, it will then pop up yet another dialog, which will select which libraries we want to incorporate into our project. So we select the Manage Current Libraries in that particular option, and then it will pop open this dialog here that shows the libraries that are currently installed on our system. So I had in this case, Crossroad Electronics, Rev Robotics, and a couple of WPILib command sets. We simply check the ones that we want for our particular application. So if we're using Talon SRX motor controllers, we would check the CTRE Phoenix. If we were using Rev Spark Max controllers, we would check Rev Robotics. These are not mutually exclusive, by the way. We can have some of our motors be Crossroad Electronics and some of them be Rev Robotics. So you can actually just check the little box up here at the top, and that will install all of the libraries into your application. If you don't use a particular library, that doesn't hurt you. So you can basically say install all the libraries, and it will only link in those libraries that you're actually using. So there's really no penalty for selecting all of them, other than a slight time delay in the build process. But as far as that's concerned, it's minimal, and you probably won't even notice it. Once the library is installed in your project, you can start using the APIs that it provides. However, you'll need to make sure that you've got the header files or the imports listed inside of the source code. So you'll say import CTRE Phoenix or something along those lines. And then that will make sure that it brings the header files in so that you can actually run the compiler. If you don't include those header files or the imports, then basically the build will fail. So at that point, you need to make sure you've got those imports listed correctly. You can then rebuild it, assuming that the build completes. Then you're at a point where you can actually deploy all that third-party goodness into the robot and start taking advantage of all your fancy new motor controllers. This particular image shows a fully functional robot written in Java. This one happens to be a tank drive robot. So with tank drive, you control both the left and the right side of the robot using two different joysticks. We see here that we have our public class robot extends timed robots. We have some private variables, some private finals here. These are Victor SPXs. These happen to be PWM controllers rather than using CAN bus controllers. But you would do a similar sort of thing with the CAN bus controllers. You'd have to make sure you imported the CTRE Phoenix code, and then you would be able to use the Phoenix CAN bus, the Talon SRX kind of controllers. We have a speed controller group on the left side and the right side. Now, this speed controller group business has changed a little bit over the past year or so. So make sure that you take advantage of the examples to see exactly how the example does it, and then follow along with that pattern. Here we see a robot init. We initialize a differential drive and an Xbox controller that we're going to be using for actually driving it. And then the teleop periodic is going to run tank drive, getting the left hand and the right hand controller sticks and using that to actually drive the robot. So this is a fully functional driving piece of Java code that will then run the robot. Again, note that I think with the 2023 release of the code, this syntax may be slightly different, but you'll still have the same basic flow. So I highly recommend that you take an example, that you look at all the examples that are provided with the WPI lib, because there are a lot of good examples for how you run the camera, how you deal with CAN bus, how you control PWM, how you deal with servos. A lot of that stuff is incorporated in the examples. So do yourself a favor, take some time to look through the examples so that you can then see how it was done before you then start asking for help from various people. Because the first thing they'll tell you is, did you look at the example? So do yourself a favor, look at the example first, and then if you still have questions, reach out and try and get some answers. And of course, one of the questions is, where do you get those answers? We have several different sources where people can actually answer some of the more common questions. Of course, one of them that I highly recommend is Chief Delphi. Go out to Chief Delphi, create an ID. It's a free ID. And Chief Delphi is where you'll find most of the senior programmers from various teams, plus a fair number of the mentors, and even some of the manufacturers, Crossroad Electronics monitors Chief Delphi, as does Rev. And so if you go out to Chief Delphi, you log in and then you select control system, for instance, and you type in your question, chances are you'll be able to get an answer very quickly, oftentimes within 5 or 10 minutes. We, of course, also have the FIRST forums. These are typically going to be where you would go about asking game questions. That's often in the FIRST forums. National Instruments has their own forum that they look at. If you're using LabVIEW, for instance, or you're having an issue with the default dashboard or something like that, then you can certainly go out to National Instruments. We also have the community site, the think tank site. These are all monitored by members of either WPI, National Instruments, or FIRST. So there's a lot of examples out there where you can actually get some help. There are also a lot of the source code. If you look at the licenses that are associated with the source code, they're all a BSD license, which is an open source license. So in many cases, teams are more than willing to allow you to take a look at their code. If they have a robot that you think is particularly cool, you can reach out to them and ask them for a copy of their code. They have the option, of course, of not giving you a copy of the code, but for the most part, most teams are more than willing to share their code so that you can then take a look at it. Take a look at it. This is all part of the cooperation mantra that we have inside of FIRST. So everybody is willing to help anybody in order to make sure that everybody has a chance to play the game. Of course, there's also some phone support for National Instruments. So there are a lot of different resources that are out there. And of course, Reddit, there are FIRST community environments there on Reddit. And you can often find a lot of examples done on YouTube as well. So take advantage of social media, take advantage of Chief Delphi. Within the social media and the Chief Delphi environments by themselves, you can probably get most of your questions answered. Okay, we have finally reached the end of this presentation. And to kind of summarize, building and wiring the robot is a challenging process. Take advantage of sensors when you can. Fortunately, FIRST provides a lot of resources so that you know which sensors do what and how best to wire them up. The use of sensors by themselves can significantly improve performance of the robot and reduce the amount of processing load, mental processing load that happens for the driver as they're trying to drive the robot. And that's non-trivial. For instance, if you have tank drive, if the robot is going away from you, the right stick controls the right side of the robot, and the left stick controls the left side of the robot. But if the robot is headed towards you, it's backwards. So that can kind of take a little bit to wrap your head around if you're a driver. The programming environments, such as Java and C++, of course, are very similar. Both of them use Visual Studio Code to build and deploy robot code. And I will say again, make sure you take a look at all the examples that are provided by WPI and FIRST, as well as the examples of third-party vendors, both Rev and Crossroads Electronics, as well as Collab, I believe, all have GitHub installations. You can download all of their examples, have them on your personal system, and then have an opportunity to kind of read through them and see exactly what they do and how they do what they do. All of that will get you started, and hopefully this presentation has been useful in getting you going as well. So good luck with the season. I will now open it up for any questions. Thank you very much for listening, and hope you got something out of it. Bye-bye.